So this was what we had discussed in the last class, right? The space segment and the space link, and the importance of the bus, the payload, and the power supply, right? The specifications involved with regards to HS376 SAT, right? Okay. And we had even seen as to the importance of having rectangular shaped wings, okay, rather than using a circular wings, and how they actually fold up. Just for the benefit of some of the students, okay, I would like to mention that the solar sails are folded up, okay, on each side uh, towards, you know, uh, which can stretch to about 67 feet, okay, which is about 20.5 meters, and they are capable of greater power output than cylindrical arrays. Now, cylindrical arrays, there can be blockage of sunlight, okay, but if it's a flat surface, then as soon as the solar rays or the sun rays falls on it, the solar cell starts charging, and it can be used accordingly, right? So cylindrical arrays are these days not considered, okay. Next, you can see that your solar cell satellites, okay, is estimated to be about 2 kilowatts, okay, where the solar cell type is more economical than the cylindrical. Now, there are systems, okay, which can actually help us getting manufactured the wings, okay, or the solar wings. So I will show you. I think in the last class we spoke about yeah. So these are your wings, okay. These are all made up of solar cells. So if it's a flat surface, it's easy to manufacture and it's easy to assemble. So this is going to fold up, okay. You can see these regions here, okay, which is actually made to fold up. So this is when it is stretched. So as I told you, from tip to tip, okay, from this tip, it can stretch to about 20.5 meters. So maintaining these high quality solar cells are very important. Okay. Can someone tell me the latest development that happened in the field of battery technology, which is actually coming up in the news 2 to 3 days, from 2 to 3 days? What has happened with the battery technology? If you're aware or if you're listening to the news, we have an update, the battery technology.
The battery charges very fastly.
Yes, of course, we do have fast chargers, but with the technology, right now we have lithium-ion batteries, right? So the technology itself has changed, and we have started implementing hydrogen-based cells. Okay, hydrogen cells. So this will actually be still faster and last longer. Okay, so we are going to see a tremendous shift in the field of automobiles, in the field of satellite designing cells, okay. So these hydrogen based, I have read an article where you have an hydrogen rod, okay, uh, which can be used for about 1,000 kilometers, okay. So these are active batteries which can actually recharge themselves. So due to the chemical process that undergoes, uh, they will be able to charge themselves, and we can sustain that rod, the hydrogen rods, for about 1,000 kilometers. So many of the top end cars, okay, around the world, they have incorporated this technology, and very soon you can see them up on roads here in our country. Okay. So attitude control, okay, is one important parameter where it refers to the orientation in space. Okay, the orientation in space. Much of the equipment carried aboard, okay, a satellite is there for the purpose of controlling its altitude. So I think you have discussed about the uh, TT and C, right? So it's about that. Just give me a moment. Go through these points which are put up. If you see that maintaining the satellite in a particular orbit or in a particular coordinate is very important. Why is it important? Because we have designed it in such a way that it can send and receive signals. Okay, the antenna subsystems should be functional so that whatever signals are propagated should reach the satellite, and this TTNC, okay, telemetry tracking and control, should actually be able to put it in place. Now, if you see here, um, now if suppose a satellite is not in proper position, then there will be thrust. Okay, thrust can be created either on the top or at the bottom or at the back or in the front. So you will have this thrust boosters. So automatically, if it's not in sync with the coordinated region, then we can actually activate these thrust boosters, and it can come back in place. So either north, south, east, west, so any direction it can actually move, and all that happens with the control of the base station, right? So in the base station we will have these controls, and so if our satellite is not maintained in a particular uh, desired distance, then we are going to lose control of these satellites. The signals are not going to reach them, right? It's necessary to ensure that the directional antennas point in proper directions. For example, Earth sensing instruments must cover required regions of the Earth. So if you have a satellite launched from your country, then we should make sure that it is actually focusing on our country, right? Some forces referred as disturbance shocks can alter the altitude. So what are these disturbances? We have spoken about a few disturbances previously, right? Can you name a few, students? What are those disturbances? Bharat, Bharat, can you name a few disturbances that can occur um, for proper communication of satellite, that can hamper a proper communication? Pranay, Sai Karthik,
Sir,
yes. What can be some
sir,
of the reasons for disturbances in communications?
rain,
Okay, good. Sai Karthik, you want to add
then
some more points to that?
thunder, and
Hmm. Fine, thank you, Bharat. Karthik, you want to add some points to it?
Sir,
Hmm. Go ahead. You're audible. Go ahead. Okay. So some of the examples can be your gravitational fields of the Earth, Moon, solar radiation, okay, meteor impacts. So all these can hamper, okay, the altitude control. So what happens if this is not maintained? As I told you, we might lose signals. We may not be able to transmit proper signals, a strong signal. So this term should not be get confused with station keeping, okay, which is the same term for maintaining the satellite in its correct orbital position, although both are same. Okay, so station keeping and attitude control both are the same, but although both are different. Okay, so next we speak about horizon detectors. So to exercise attitude control, there must be available some measure of satellite's orientation in space or any tendency for this shift. So we should have a point of reference to know if it is shifted or not. In one method, infrared sensors, which are known as horizon detectors, are used to detect the rim of the Earth against the background of space. So what is a rim? Rim is the circumference, right? The exterior circumference. So we take that as the reference and using our infrared sensors. Now students, keep in mind your satellite will have a lot of sensors. The reason is because it is somewhere there out in space, and we need to develop those minute electronic subsystems which can actually respond to few information. Okay, if suppose the temperature is high, then what should happen? Okay, if I want to move the satellite away, uh, if it's away off track, and how do I bring it on track, right? All these are possible only with high efficiency sensors. So if you're thinking of working in core area, okay, then this can be your research line. Okay, you can work on sensors. You can work on miniaturizing the sensors, how to send and receive information with minimum size. Okay, and how to make it work with minimum voltage. See, working with power module is actually very much important, power consumption, because as you know, eclipses can last up to about 72 minutes, right? From few minutes to about 72 minutes, which means from few minutes to even hours. So during this moment, they are highly reliable on their own inbuilt batteries, right? So due to which what happens, if the batteries are not efficient, if the power management is not fine, if the device is connected, if the sensors connected draw in more potential, okay, then it's going to be difficult for the power supply or power management unit to actually help in getting proper power distribution and making the best use of the battery available. Okay, so with the use of such sensors, one for each quadrant, the center of the Earth can easily be established as a reference point. So I will have sensors, okay, the rim of the Earth. So immediately I can find out what is the center of the Earth. Any shift or in orientation is detected by one of the sensors, so it can find out if there is a shift, okay, small shift, and corresponding control signal is generated, which activates a restoring torque. So torque is nothing but the the boost that happens, okay, the thrust that happens, and the satellite comes back in place. So maneuvering, okay, this is another new concept, okay, where we will be discussing as to how these satellites are handled. Usually attitude controlled process takes place on board satellite, but it is also possible to control the signals to be transmitted from Earth. So these are called base station. Based on attitude data obtained from satellite, how do we get this data from the satellite? Based on the sensors. So the sensors will exactly tell us where it is positioned, either is it on track or off track. And then once we receive this information, we get to know, fine, this is not proper. So we will send back another signal saying that you have to come back on track. So who will help us with this? The sensors are going to pick up the signals and they're going to restore it back to the proper segment. Okay. So passive attitude control refers to use of mechanisms which stabilize the satellite without putting a drain on satellite's energy supplies. Okay, so as I have mentioned, your power management unit is a very important unit which can actually uh, play a major role in deciding where your satellite sits. So these thrust jets are impulsed to provide corrective torque. Examples of passive fluid control are spin stabilization and gravity gradient stabilization. So there are two important parameters here: the spin, okay, when it rotates about itself, north to south axis, and the gravity gradient stabilization. So the gravity gradient stabilization depends on the interaction of the satellite with the gravitational field. Now this can be as to how near it is from the earth, how or what's the distance between the satellite and the moon, okay, the solar flares, the solar winds. So all these are very much dependent for the gravity gradient stabilization. For communication satellites, spin stabilization is often used. So those satellites which are actually sent exclusively for communications, so we make sure that the spin is stable. It is just like a top. Okay, as soon as you put the rope and then you play with the top, initially there is a spin. Okay, initially it is not stable. So as it keeps spinning, it starts becoming stable. So you will find that the top is just standing, but it's actually spinning around its axis. Fine. The other form of attitude control is active control. Okay, active control. So with active control, there is no overall stabilizing torque present to resist the disturbance torques. Instead, corrective torques are applied as required to respond to disturbance torques. So these are real-time data which keeps getting pulsed out from the sensors, and once our base station is able to sense these real-time data, okay, so they will be able to know as to in which coordinate they are present and accordingly send corrective measures. Okay, so it is just like if you're moving forward at a speed of about 40 kilometers per hour. Just an example. Okay, so if there is another force acting in the opposite direction, it is as good as applying a brake, right? So these kind of corrective measures, these kind of torques or jets are applied in order to bring it back in proper space. So the methods used to generate active control torques include momentum wheels, electromagnetic coils. So these are all involved. All these are involved inside your uh, device, okay, inside your payload. You have your coils and you have your mass expulsion devices, gas jets, and ion thrusters. So this EM coil, this electromagnetic coil, works on the principle that Earth's magnetic field exerts torque on a current carrying coil. Okay, so you should get back to your concepts of physics. So whenever there is a current carrying coil, okay, you have E fields and H fields, okay, which are perpendicular to each other. So E is your electric fields, okay, magnetic fields, H, and that this torque can be controlled through control of the current. However, the method is of use only for satellites relatively close to the Earth. Say, for example, the satellite is too far from the Earth. Then what's going to happen? This magnetic effect is not going to happen with the electromagnetic coil. It's not going to work out, right? Fine. So there are three axes, okay, which actually defines the position of a satellite. So what are they? These are nothing but your roll, pitch, and yaw. Okay, roll, pitch, yaw. So first let us look at the diagram and then we will get back to the explanation. So this is my pitch rotation. Okay, pitch rotation. Roll is in this fashion. Okay, and my yaw is in the other direction. So this is towards the center of the earth. Yaw is actually facing to the center of the earth. Okay, the pitch axis is normal to orbital plane. What is the orbital plane? If you slice the earth, okay, so that's going to be parallel to it, and this is your roll axis. Fine. So this is your pitch, yaw, and roll. Okay, so these three axes are important in order to maintain the satellite's position. All three axes pass through the center of gravity of the satellite for an equatorial orbit. So the first one that you have to see here is movement of satellite about roll axis moves the antenna footprint from north to south. So when there is a roll, okay, when you have activated roll, okay, so the antenna moves from the north to south. Okay, whenever there is a roll action happening. Movement of satellite about the pitch axis moves the antenna east and west. Okay, so about the pitch, it is east and west, and about the roll, it is north and south. Movement about the yaw axis rotates the antenna footprint. So the antenna is rotated when we look at yaw. So pitch is your north and south, roll is your east and west, right? Okay, and your yaw is about your antenna footprint. So that's the figure talking about the roll, pitch, and yaw axis. The yaw axis is directed towards Earth's center, right? Uh, and the pitch axis is normal to the orbital plane. The roll axis is perpendicular to the other two. So all these three are perpendicular to each other, okay, causing a 90-degree between each, okay, X, Y, and Z axis. Spin stabilization may be achieved with cylindrical satellites. So here, this is one advantage of having a cylindrical type of satellite. So if we have a rectangular or probably a square shaped satellite, maintaining that spin, okay, the rotation is going to be difficult. But if in case it is cylindrical in shape, so the wobbling effect is less, is considerably less when you consider your cylindrical type of satellites. The satellite is constructed so that it is mechanically balanced about one particular axis and is then set spinning around this axis. Okay, so first we bring it in the proper coordinate, and then we make sure that it is stable there, and then the spin starts. So how do we start this? Based on roll, pitch, and yaw. For geostationary satellites, the spin axis is adjusted to be parallel to the north and south axis of the Earth, as illustrated in the figure. Right. So these are our satellite path. Okay, so this is our geostationary orbit. As I told you, this is like a gold mine for all the satellites. So if your satellite is in cylindrical form, okay, it becomes easy to maintain the stability. So there is no wobbling effect much. Okay, spin is initiated during the launch phase by means of small gas jets. Okay, so these jets will have a small amount of gas in it. Okay, and accordingly, as soon as these jets are, in action, so it will rotate along roll, pitch, or in absence of disturbance shocks, the spinning satellite would maintain its correct altitude relative to Earth. Disturbance shocks are generated in number of ways, external and internal. So disturbances can be in the form of solar winds, can be in the form of probably a meteor coming and hitting the satellite, right? Any other things. So this we have already seen, right, with respect to the spin stabilization, okay, and the geostationary orbit. Right. Use the angular momentum of its spinning body to provide roll and yaw stabilization. So for a minute, okay, it revolves about 50 to 100 times. Okay, so you can imagine the amount of speed of spin. Okay, solar radiation, gravitational gradients and meteor impacts are all example of external forces, as I told you, right? Which can give rise to disturbance shocks, motor bearing friction, and movement of satellite elements are all causing disturbance, and these are all internal because of the systems involved inside the satellite's payload. Okay, in the payload, the overall effect is the spin rate, and that's going to decrease, and the direction of angular spin axis will change. So once there is a change in the spin, once there is a change in the angular position, then it's going to be off track for sure. So these impulsive type thrusts are actually used so that we actually get a proper uh, correction, and it comes in north-south orientation. Nutation, okay, this is a term that you need to look into. Nutation, which is a form of wobbling and can occur as a result of disturbance shocks and misalignment or unbalance of control jets. So I can ask a question, what is meant by nutation, and use a diagram and explain the same. So what you can do is you can use this roll, pitch, and yaw. You can use the diagram of the geostationary orbit, okay, and you can have your explanation for the answer. The nutation must be damped out by means of energy absorbers known as nutation dampers. So that should be nullified. These disturbances, wobbling disturbances, should be nullified with something called dampers. So this is one such example, okay, for your HS-376 spacecraft, which was, as I mentioned about, this company Hughes, okay, Hughes aircraft company, which they have done a tremendous effort those days in getting these things configured in manufacturing and collaborating and launching into the space. So these are some of the uh, parts that you can actually look into. So you have a telemetry here, okay, which is for your tracking, okay, and command center. So this small device will actually send the signal for your satellite. So you have this antenna feeds, thermal radiator, control thruster, propellant tank, which means used as a fuel. Okay, fuel initially when you launch the satellite, before you could launch, you fill some fuel and then launch it. Okay, so that's the propellant tank. Then apogee kick motor. Okay, in order to um, make sure that it is in proper orientation. Then you have your solar cell arrays. Okay, then you have your battery pack. Okay, so once this battery pack is there, it makes use of it when it's not in supply. Okay, then you have this traveling wave tube amplifier. Okay, in short, it's also called TWT. Okay, and you have a repeater shelf here, and you have thermal radiators, as I mentioned previously, and this solar cell arrays are going to be uh, used when there is going to be sunlight, and batteries are going to be used when there is absence or when it's in eclipse mode. Okay, so this is one such example. Okay, you can see that it's a Telestar 3, the name it as Telestar 3. Okay, you can see that this Telestar 3 and communication satellite, which is shown without its cylindrical panel. The satellite is built for the American Telephone and Telegraph Company. So you do not have that exterior panels. Okay, so these are the internal structures. So you can see that how complex things are, and how that it's working. Uh, this is the receiver. Okay, the antenna receiver. Okay, so the momentum now, momentum wheel stabilization. As I spoke to you about, the satellites are to be stable without the wobbling effect. So the gyroscopic effect of spinning satellite was shown to provide the stability for satellite attitude. Stability also can be achieved by utilizing this gyroscopic effect of a spinning flywheel, and this approach is used in satellites with cube-like bodies. So sometimes we wouldn't have satellites, okay, which are in the cylindrical fashion, right? We might have satellites which are in the form of square, in the form of cube, right? So for those satellites, how do we maintain this wobbling effect? And this approach is used in satellites with cube-like bodies. They are known as body stabilized satellites. The complete unit, termed a momentum wheel, consists of a flywheel, the bearing assembly, the casing, electric drive motor, and associated electronic control circuitry. So what does this electronic control circuitry involve? It will involve the sensors. The flywheel is attached to the rotor, which consists of a permanent magnet. Okay, so this is what you should actually look into. This is a three-phase set of a stator. So you can find the front-end connections. Okay, the back-end connections are used with a dotted line. So I have picked up this from the Encyclopedia Britannica. Okay, and to show you the diagram as to how this motor uh, stator is actually connected, a three-phase motor stator. Okay, so it's connected to a magnetic field for motor action. The stator of the motor is attached to the body of the satellite. So which is the stator? This stator is connected to the satellite, and this motor provides the coupling between the flywheel and satellite structure. Okay? So which means there is to be speed and torque control of the motor, and that is exercised through the currents fed to the stator. The housing for the momentum wheel is evacuated to protect the wheel from adverse environmental effects, and bearings have controlled lubrication that lasts over the lifetime of a satellite. So these bearings that you see, okay, these bearings that you see, these ball bearings, are to be maintained in such a way that it is lubricated very little and how much ever is required, so that they don't wear out and they come for at least 15-20 years, which is a normal lifespan of a satellite. Okay, so these are about your roll, pitch, and yaw. Okay, so internally you can see that these are the jets involved, the thrusters that is involved in all the directions. Okay, so across roll, across pitch, and across yaw. So you're able to visualize things, right? Students, you're able to follow?
Yes, sir.
Okay, fine. So you have your pitch, you have your roll, you have your yaw. So these thrusters, okay, these thrusters are embedded in your satellite, and then you have your sensors. Then you have your um, coils which are getting connected. Okay. So it's a complex thing actually, you see. Okay, so these sensors are picking up data and they're trying to meet. So we were discussing about the momentum wheel stabilization, right, which happens across the roll, pitch, and yaw. Fine. So as you can see in the diagram, you have different thrusters. Okay, for roll you have different thruster, for pitch, and for yaw you have different thrusters. So you have these wheels, okay, which actually helps enabling the satellite to be in. So this is a three-axis stats. The body remains fixed relative to the Earth's surface, while internal subsystem provides roll, and yaw stabilization. So the internals, okay, what are those internals? All these yaw wheels, roll wheels. So these will maintain along with the thrusters and make sure that it's all in place. Okay, fine. So the term momentum wheel is usually reserved for wheels that operate at non-zero momentum. Okay, so if there is no momentum, okay, so we can term them as non-zero momentum, which means there's no movement. Such a wheel provides passive stabilization for the yaw and roll axis. Okay, so zero momentum makes sure that it is as stable as possible. When the axis of rotation of wheel along the pitch axis as shown in figure, okay, that is the previous figure that we spoke about in the C, okay, C figure, this figure, okay. Control about the pitch axis is achieved by changing the speed of the wheel. Okay, so you can see that in A diagram, the first one, our control is happening with the help of these thrusters. Okay, with these thrusters. When a momentum wheel is operated with zero momentum bias, it is generally referred to as reaction wheel. So we call them reaction wheel if in case there is a error. What error? Error in its position. Reaction wheels are used in three-axis stabilized systems. Here, as the name suggests, each axis is stabilized by a reaction wheel. Okay, so you can see that exclusively in figure C. Okay, so for pitch you have a wheel, for yaw you have a wheel, and for roll you have a wheel. Okay, so each wheel corresponds to each direction. So you can see that, for example, if we say that this is from north to south, okay, this is from east to west, and this is the other direction. So all the three X, Y, and Z directions are maintained with the help of these three wheels, which is the roll, pitch, and yaw. So how are these activated? Based on the sensors. Once the sensors gets data, so these electromagnetic coils gets activated, and once these coils are activated, these motors or the stators, okay, as I showed you in the previous diagram, these are connected to the satellite and the ball bearings start working. So once it starts working, the lubricated ball bearings, and these wheels start rotating. So once it starts rotating, it makes sure that it is in place. Okay, so next the next topic will be about station keeping, which is a little huge topic. So we will limit our discussion to this topic here, okay, which is about the momentum and how we have stabilized using the stator, and what is called as body stabilized satellites, and the advantage of having cylindrical satellites, the advantage or disadvantage of having cuboid uh, type of satellites, what are the internals involved, right? So all this we have discussed so far. So students, you have any doubts with regards to stabilization, spin, roll, pitch, yaw, anything as such? Any doubts? Any doubts so far? Yes, any doubts? If any doubts, we can have a discussion. If not, we can end the meeting now. Any doubts, students? Okay, so I've got a confirmation